And I would like to introduce our first speaker. It is Martin Punke, like representing, like when actually we are thinking how to set the program for this workshop, one of my colleagues came and say, oh, I saw a very good presentation at one of the events about automotive imaging and AutoSense. And it was called, how was it, 10 years of automotive camera. So it was 10 years of CIVIT, 10 years of automotive imaging. So it was a very good fit. And thank you very much, Martin, for joining us. And the floor is yours, please.
Thank you very much. And thanks for the invitation. So it's really good to be basically back in Tampere. And I will talk about a decade of automotive camera technology. Actually, I'm working in the automotive area for a little bit longer. Yeah, just some words. I studied at the university, and then I actually joined Nokia mobile phones. So I was working in the Ulm R&D center, doing illumination technologies, flash and camera topics. So at that point in time, I often came to Tampere, so it's good to be back. And then when the R&D center closed in Ulm, I started basically the imaging topics inside Continental. That is now going to be Aumovio, and I'm saying a few words on this. So there we are working on basically camera hardware for the exterior cameras mainly, but we're also doing image quality topics there and also camera sensor modeling. If you want to learn a little bit more about autonomous driving, assisted driving, there's even a book out. We contributed with the chapter on camera hardware. So, but it's a really thick book. So you can learn all kinds of stuff of radar, stereo vision, all kinds of other topics around that. So not only sensorics, but everything else. It's also open access from January onwards. So if you want to check it out, please do so. Then a few words of what is Aumovio. Actually, you might know the company Continental, so it's one of the biggest tier ones in the automotive sector. But in the meantime, they wanted to concentrate it back on the tire business and basically spun off the automotive electronics sector, and that's where I'm working on. So here we are doing basically everything you can see inside the car, sensing topics, networking topics, body control, user experience, so displays, interior camera, all that stuff. So I'm coming from the autonomous mobility area, where we're doing basically everything to do with ADAS, autonomous mobility, from sensorics, cameras, ultrasonics, radars, to processing units. That is basically also the trend. I'll come to that in a minute as well, how the automotive industry changed over the past years. So what can you expect for my talk today? It's a bit of a biased view to some sense, of course. Yeah, we are in the automotive. I try to keep an eye on other industries, but I will focus on the automotive technology also giving some insights on the past and of course also a bit of an outlook into the future. So that is the agenda for today. I talk a little bit on the automotive market, bit on system architecture, camera technology, and then also on the future. So what were we doing 10 years ago? At that point in time, I also gave a speech, and basically already at that point, we were basically saying, yeah, we will have fully connected cars, fully sensorics all around the car, front, side, and so on. And that's actually really what's happening these days. So at least in the high-end cars, there are lots of sensors, cameras, radars, lidars, that is really sending all the environments around the cars. Also at that point in time, we were predicting a little bit on what is going on in the autonomous area with different steps at that point in time, like autonomous parking, emergency brake assist, and so on and so on. So all these functions you can basically buy today in at least more modern cars or higher end cars. But it's really dribbling down also in the normal car. So emergency brake assist is a standard feature these days. Also backup cameras, front cameras are basically standard. What did not happen as predicted 10 years ago was the fully automation. So that really took longer. So you don't have like fully autonomous cars, at least not in the normal passenger cars. Of course, you have robotaxi business. And that is also something that changed a little bit from like 10 years ago. There it was all about robotaxis. Yeah, Waymo was being there and many other companies. Many of them are not existing anymore, actually. That is also one of the changes that happened over the 10 years. So many companies that were in this field are not existing anymore. Waymo is still there, and they are now actually only now really ramping up their robotaxi business, as you might have seen in the news. What happened in the meantime is that there was a bit of a focus shift towards also robo trucks. So robo trucking is now, not maybe a hype, but another business area beside robo taxis that is taking off quite nicely. So we are partnering with Aurora, but we are also providing sensors to other companies. And that is, they're already starting now. So they have running autonomous driving, autonomous trucking. It will probably really take off in like 1 or 2 years, where they really extend also their fleets. So not only Aurora, but also other companies are doing this. So then a few words on the automotive market. So maybe that's also interesting to see what happened here, because that is also changed quite a lot. We saw 10 years ago, it was pretty much standard business from Tier 2s providing components, lenses, image sensors, Tier 1s putting it together, providing the sensor system, doing some software evaluation, and then providing it to car manufacturers to build that into the car. Then 5 years ago, roughly, things changed. What happened is that there were other providers, mainly SoC providers, CV stack providers, that were also providing parts directly to the car manufacturers, because some car manufacturers also started to be more vertically integrated. So they picked different pieces, sensors from us, CV stack from someone else, and put that together or build them by themselves. And in the meantime, it is basically all over the place. We have component manufacturers, Tier 1s, Tier 2s becoming Tier 1s, CV stack suppliers, SoC providers, system providers, and everyone is partnering with everyone, and everyone is competition to everyone. So it's a nice, diverse market in the meantime, and it's sometimes quite hard to see who is working with whom, who is partnering with whom, and who is competition of whom. So interesting, but much more complex than 10 years ago. Then let's dive into the system architecture. What happened here is basically that we were going from smart sensors, so sensors that had the sensing part, but also the processing part in one box, going away to the centralized processing architecture. So we still have smart cameras, we still have smart radars, but in the meantime, many topics are processed with a heavy SoC, with the software stack, and then different sensors are providing basically raw data into that SoC, where the processing, computer vision, perception stacks, and driving stack is then happening. So that was a major shift, and it is also, especially for higher end systems with many sensors, that is the architecture of choice today. There are still, the basic systems are still working with smart sensors, but the higher end system more with a centralized system. And also on the camera side, we really saw that many, many more cameras are installed in a car. 10 years ago, it was mainly, even in the high end, we had maybe one camera, sometimes a stereo camera system to the front, maybe a backup camera, but that was basically it. In the meantime, we have like 5 to 6 is becoming more or less standard. So we have a higher resolution, wider field of view front camera. We have surround view fisheye cameras, maybe a back camera as well. And then these days, the high-end equipped cars are having more than 10 cameras. So again, fisheye for the parking area, and then higher resolution for the further sensing to the front, but also to the sides, to the rear. So there are cameras basically everywhere. And in addition to this, there are interior cameras, so driver monitoring cameras, occupancy cameras. So there's even like a 1 or 2 more cameras inside the car as well. So overall, quite a lot of cameras that you can put into the car. And that was driving the growth on the market as well. So here you see the growth on camera modules produced for automotive. So we are at roughly 250 million a year. And it's further growing. As you can see, more cars getting equipped with these things. So things are growing a lot. If you compare that to the mobile phone area, that is still this tiny little bit down there. So comparable on volume side, it is still small. Yeah. So there are much more mobile phone cameras, even though in some of these modern cars are more cameras than in a even modern mobile phone, where also the amount of cameras increased quite a lot. And you see that picture, so I took some of the good old Nokia mobile phone cameras that I still had in my drawer. And the right side is one of our optical modules. It's actually only a 1 megapixel optical module. In the meantime, we have higher amounts, but just to give you a bit of a comparison on the size. Yeah. So in automotive, it's all about cost as well, as in the mobile performance, but the size is not as squeezed as in the mobile phone. So we have a bit more space to work with, which is sometimes quite nice. So these are things you see on, we call it satellite cameras. So these are these remote sensors, raw sensors that you can put around the car. So they are a little bit heavier, but really robust for everyone in the car. I'll talk today a bit more in detail on the camera module side, on the hardware side, where I'm working on with my team. Not so much on the processing side, though there will be some more talks by Frederick and Peter going more on the computer vision side and the simulation side. So I concentrate mainly on the camera hardware. And here I will start with the optics, because that was also something that evolved over the years quite a bit. So optics is, of course, old story. Nothing is evolving anymore, but it's actually not really true. We have seen the change from a smaller field of view, low megapixel, to really large field of views in the front of the car. So also special distortion profiles were used here to have like more resolution in the center than in the corner. So quite a nice optical technologies were involved. And then we saw also that we have many more cameras, as you see, with different field of views around the car. So these days we are dealing in my group alone with more than 20 variants of camera optics. And 10 years ago it was maybe 1 or 2. So that is really ramping up quite dramatically. Enabling on this was basically advances also in the optics still. So there is still advancement going on, better glass molding, better plastic molding, better coatings, more automated assembly. So many things that you also saw on the mobile phone is trickled down to the automotive with a bit different emphasis probably, but really giving us in the automotive technology area better performance for smaller megapixels or smaller pixel sizes, lower f-number lenses for low light performance, better stray light performance. So that is actually a very hot topic in the automotive, that we don't want to have stray light or ghost effects in our optics to avoid any like false detections, and so on and so on. So everything improved step by step. And one thing that is also very important in automotive is robustness over temperature and over the lifetime. So we're talking about like 10 years in the Volvo truck business, or in general in trucking business, even more, like 15 years lifetime that the optics has to withstand, including the coatings, including everything. So that is really a challenge to keep everything nice and performing over that time period. Then on the image sensor side, of course, that was evolving even more rapidly, as normally with going with the semiconductors, there's quite a rapid process. And we also had a megapixel race in the automotive to some extent. So not really by promoting it to the customers, so maybe some are mentioning that they have a HD camera or something like that, but more it just happened from performance and high resolution needs of the camera processing part. So some years back, we started basically with 6 micron pixels, went down to 3, 2. Nowadays, it's quite common, and it is going further down. On single pixels, so actually we have a technology called split pixel, where we use smaller pixels to extend the dynamic range. So here we're basically also using the mobile phone pixel pitch of 0.8 or something microns for the smaller pixels. So it's still, again, nice move between the industries, mobile phone, automotive, industrial sensors. So everyone is doing something that the others may need or not need in the end. And that is the image sensor providers are happily to move around the industries. And here another slide on the technology. So we introduced BSI, something that, of course, in the mobile phone was happening a bit before. We have stacked sensors these days. What was very important for automotive, that we have high dynamic range sensors. So that was in the beginning by multi-exposure HDR, then we had dual conversion gain, and these days we have even more like split pixels, low fix, you name it. So the dynamic range extended quite dramatically. I will have another slide on this. Beside the pure performance, there was also a lot of functional topics going into the image sensor. So in automotive, it's important that we talk about safety, we talk about functional safety, cybersecurity, so stuff that is really needed in the automotive area to have the best performance and safe performance over the years. LED flicker mitigation was a very hot topic over the past 10 years. So how to mitigate all the flickering light sources, or to avoid that you miss basically a red traffic light. That is basically the horror scenario, that you're running over the red traffic light. So what can you do to avoid a missing or false positive here? Then on the performance, as I said, there is advancements in SNR. So these days, these image sensors are getting really good on noise performance, so read noise, temporal noise. It's all very, very nice, but actually it's a little bit flattening out in the performance. What is still going on performance increase is the HDR range. So 10 years ago, we had basically 80 dB dynamic range by some means. In the meantime, we had basically having 120 dB. And if you plot that on a linear scale, it's quite amazing how that evolves. So these days, we are talking about 140 dB of dynamic range that we utilize, at least to some extent, on some extreme scenarios, especially at night. We have bright light sources, so headlights from other cars, for instance, but you still want to see a pedestrian in the woods, basically. That is the use cases that we see for the high dynamic range imaging. So such a sunset is still medium range dynamic range, so that's not even the most challenging one that we see. Another topic that we looked in the automotive area as well is what is the best CFA? And basically there's no conclusion in the market. Everyone is using something else. Many folks are still using RGB, still state of the art, the ISP optimized for that. It has also still some very good performance, but they, especially for the machine vision part, people worked or still working with different color sensors like RCCB, RCCG, RYYCY, so quite exotic topics as well. They all have their pros and cons that are listed to some extent here. So it's really about how did you optimize your system? Is it working with that CFA or not? But we also saw that many things fall back to RGB in the end because it's just easier to use overall. Yeah. Then a bit of a special topic is manufacturing. So often you don't see a lot of things about manufacturing, but just to give you a bit of an insight, what we are talking here in our industry on the manufacturing side as well. So the challenges and steps are shown here. We're going from PCB manufacturing, and that is basically all about product variations, robustness, size, cleanliness, over the lens alignment, which is one of the most challenging one in the automotive area. I'll come to that in a second. Sealing, so our cameras have to be tight, and they have to be tight at production, and they have to be tight against environmental conditions over 10 years. So that is a hot topic. We test them quite extensively, electrical, optical tests. And then calibration is another topic, especially for the multi-camera systems. We have to have a really nice intrinsic calibration so that the customer or ourselves on the system side can use these cameras in the best possible way to do stereo imaging or other stitching algorithms. Let's jump a little bit into the lens alignment topic. And basically, if you're working in the camera area, you know that you have to focus the lens to the image sensor on a micrometer level. But what we can't do in automotive, or at least not yet, is doing autofocusing. So, of course, the mobile phones, you have fixed focus cameras, but usually these days it's all autofocus. So you don't need to take care in production so much of a perfect focus that you need to hold. So you can always adjust the focus afterwards. This is something we're usually not doing in the automotive area. So we have fixed focus cameras, and they have to be fixed and perfectly aligned for, again, the crazy environmental conditions. So from -40 up to 85 or even 100 degrees. So a huge temperature range that we need to have that fixed. And then, again, the long lifetime. So there cannot be any lifetime shift. There cannot be any thermal shift. So we have to do a lot of tricks and squeezing and optimization to get a nice stable focus over that environmental conditions. And it's actually also where we lose basically most of the money in our production, because that is really hard to achieve. So we have to be very precise, otherwise we will not meet the MTF requirements of our customers, and then we need to throw away the cameras, which we of course want to avoid. So going a little bit away from the hardware, I'll talk a little bit about sensor modeling as well. Because that is something that we were working even in my group and the hardware group basically as well. Because in the beginning we wanted to basically mimic our cameras as good as possible, also to model what we need for the future. In the meantime, it's more focused even to supply the sensor model to our customers, to our system colleagues, for them to have a basically virtual simulation pipeline going from virtual scene creation, using our camera model on the optics and image sensor side, and then running their algorithms on that. So everything going on sill or hill level, but maybe making it more virtual, making it faster, making it easier to check what's going on. And for that, we have very sophisticated modeling for the lenses, modeling for the image sensors. We're doing some in-house modeling, but we're also working with the image sensor providers so that we virtualize basically a full camera for the simulation areas that any customer or any system guy can use then in the end. And that's looking roughly like that. So these days, you have lots of render engines. So you can use Unreal Engine, you can use Unity. There's a few other providers in the automotive space that providing you with render engines. There are other topics coming along as well, how to create a scenario. But this is like the old school traditional way to do it. And then we add basically the optics around it. So we add distortion, sharpness, and so on, and the image sensor as well. So noise, color correction matrix, and the output is a raw image that then can be fed into the computer vision algorithms or the ISP if you have that in hardware or in software. So what's next then? There's still a few things to do, so we are not done yet. What is basically happening today is that at daytime, we have already quite nice performance. We have more or less enough resolution, enough sharpness, but it was still not good enough for all scenarios, for all things is night or bad weather conditions. This is still something that the industry is working on by either increasing the performance of normal cameras or using new sensing schemes, new wavelength ranges. So that is something of a hot topic, how to make the cars also safe at night or driving autonomously at night, because that's still not so easy. Then another topic is availability. So of course you don't want to run around your car and always clean your cameras all the time. So how can we keep them clean? By coatings, by washing solutions, by other solutions. That is also a topic for our customers to avoid that the end customer is having too much trouble with using their cameras in the cars. Computer vision, another hot topic. So there's a lot of stuff going on still here. So it's not done yet on the perception side, but then also on the full driving stack side. So probably we'll see some stuff of that later on in the other talks as well. And last but not least, lower cost is a topic. You saw that we have so many sensors these days. So our customers, but also the end customers, of course, don't want to pay 10,000 euros for a sensor set or for a driving or autonomous driving feature. So we have to be mindful about how can we optimize the cost of the single sensor, of the system, of the connections, of the whole setup, so to give best value for the customer. And then lastly, the market is also giving us some more challenges besides the technology itself. So there are geopolitical tensions that is driving some more regional approaches. So we have to provide now cameras for the US customers that may be looking differently to cameras that we provide to Chinese customers or to European customers. So that is on the supplier base quite a headache these days. We have different market speeds in EV adoption. So it's not that the EV has no different cameras than a combustion engine car, but the platforms that EVs are working on are usually a bit more modern, more centralized architectures. So if the customer is then prolonging their combustion engine platforms, that might delay also some introduction of new technologies, or we have to retrofit on combustion engine platforms some of our more modern systems. So that is making everything a bit more complex and also a bit more unpredictable when and how the customer really wants to go into into the market with their systems. Ownership model changes, touched on that. So if we have robo-taxis, if we have robo-trucks, there might be completely different business models for us as tier ones, but for the customers who is owning the robo-taxi, is that a private customer or is that a fleet management system? Are we selling our products or are we renting our products or are we getting paid by miles? So there are different models of monetization these days. And then something that we're also looking at, is there something else than automotive? So like normal passenger cars. I mean, that's one reason why I'm also here to look and talk to people of other industries, like special vehicles, agriculture, mining, forestry, industrial is a topic. So moving platforms. So we have also some prototypes on that with our sensors. Robotics, humanoid robots, maybe they're taking over. They need a lot of cameras and other sensors as well. And last but not least, we saw that before, the defense area is of course also something that is growing, that also needs sensorics. That might be a market for the camera guys as well. And with that, I would like to thank you.
Yeah, thank you, Martin. We have time for questions. Like, I will go like this. So.
Kai Hämäläinen, Tampere University. So very nice presentation. Thank you. I heard that already yesterday evening there in Paidia. Thanks. The question is there that there will be a lot of data processing in automotives in the future. And what we can do here at Tampere, we have this system on chip development, SoC development. Roughly 6% of the talents in Europe, they are located here. So we are ready to make collaboration with you with the SoCs.
Yeah, I think it's a lot of stuff still to do, as I mentioned. It's not done. It's on the sensoric side, there's still a lot of things to do on the imaging side. So we're looking at different sensor modalities. And then, of course, on the processing side, hot topics are like how to transfer data. Yeah, are you transferring it in raw or maybe in a compressed matter? How do you process data? How to provide power to the chip? So there are many different topics that you still can optimize and make better on these systems. So there are still, I think, quite a lot of things to do. Yeah.
Okay, thanks.
Hello. Teemu Rytkönen, Unique. So the robo-taxis, robo-trucks, do you see that the blocker for autonomous driving is it a technical problem still to be solved, or is it more of a legal problem to be sorted out?
A little bit hard to say. I think it's to some extent both. I think technology did solve many of the former problems. So as I said, perception is nowadays quite robust. The cruising functions are quite robust. They're still evolving, so it's still getting better. The legal frameworks also still need to catch up. But this is also then again very regional. So where do you look? Do you look to the US? Texas, you can always go. California can already go. In Europe, it's all restricted. In China, you can do things. So it's everywhere. It's a little bit different. And then what I see in many of the discussions also over the past 10 years is how safe do you have to be? Yeah, how you can prove safety, and that is getting tricky with end-to-end learning and so on. So how do you prove that your new networks is doing the right things? So that is, I think, a hot topic. That's not my proficiency, but probably learned something about that in a minute. But there was a hot topic also in all the conferences I attended is, do we have to be as good as a human driver? Do we have to be as good as 1,000 human drivers or 1,000 times better than a human driver. So what is the tolerance of the society on failure that may occur? And they will occur. You cannot really simulate everything out. So there will be still a probability of something going wrong. And are we able to accept it? I think that is still a bit of an unsolved question. How much of a failure would we actually accept? Yeah? Of course, everyone is trying to make it as safe as possible, to have minimal risk maneuvering, fast stopping, but you cannot really solve each problems. And you see that with the news from Waymo or so. Even if they run over a chicken or whatever, you would say there's a bit of an outcry. Yeah? Sometimes there's a big outcry if someone is doing one and some others are doing something much worse wrong, and I will not name some companies, you can maybe imagine, and there's not such a big outcry. So it's all perception as well, yeah, in this industry. So
Thank you.
no clear answer, but still something that we have to solve somehow.
There is another mic there. Alessandro.
Okay, Alessandro Foi, Tampere University. Two questions. So you mentioned that there is still a lot of work to be done towards realistic simulation of sensors, and so my question would be: so what aspects are currently lacking in current modeling? And the second question that might maybe be related to this is in many of the challenges that you mentioned, it seems to me that, for example, in the infrared wave bands, some of those problems do not occur inherently, and I'm aware that there are already a lot of works towards the adoption of particularly long wavelength infrared in automotive. So what's the limiting factor currently in the industry for the wider adoption of thermal infrared in automotive?
Let's start with the second question, cost. And the customer, they don't want to add another sensor set. So that is basically one of the reasons. There is technical solutions, long infrared. We are also looking at different wavelengths. But there is some reluctance to add another sensor set. So we saw that with LiDAR. Yeah, there was a big hype 10 years ago. Everyone wanted to install LiDARs. And they are in some cars, but mainly in China. In Europe, you only see a few cars going around with LiDAR. So everyone is still trying to make things work with camera and radar, let's say. These are the basic sensor sets these days. And radar is evolving, camera is evolving. So then the question is always, if these traditional sensors are evolving more and more, do we really need that other sensor modality? And how much do we want to pay for it? That is one of the reasons why it's not really adopted yet. And quickly on the sensor modeling side, I think our sensor model is actually quite sophisticated, quite good. That is not really the problem to make the sensor models better. It's actually the scene generation that is giving us more the headaches. How to create the scenes more realistically, to have more modalities, more variations, and also to include all the geometric, temporal, and spectral information that you would need for your sensor models. Because the render engines are only so realistic these days. So there is still a lot of things are missing, especially on the temporal side. So you cannot really mimic LED flickering or rolling shutter effects, or at least only with a few render engines. That is still a bit of a problem. And in the meantime, there's generative AI topics popping up that is questioning a little bit the whole approach with the normal learning engines, I would say.
Thank you.
Okay, I suggest we move forward. Thank you once again to Martin and to questions.